help you with a 2.4 worksheet, I want to make sure that when you're taking a look at this, after you've watched the Ed puzzle and you have your notes in front of you so you can use your notes to help you with this, that you get an idea, more of a feeling, like more of a logical progression to figuring out whether you should first of all have a physical or a chemical change. So let's go through a couple examples. I'm not going to do all of them, obviously, because I want you to take a stab at them without having watched this screencast first. So cooking an egg, is that a physical or a chemical change? What you have to ask yourself is, do you see like an actual visible difference between what the egg was before and what it has become, like its new thing? And if it's a new thing that the structure of the egg has changed, now you got to be careful. There are some very there's some very common examples of like water changing into ice, and you're like, well, hey, I see it change. You know, it looks like it changed. That doesn't actually change the composition of the formula of water. H2O is H2O, whether it's a liquid or it's in ice as a solid. It does look a little bit different, but we know that its actual structure doesn't change, that it's still 2 hydrogens and 1 oxygen. However, the molecules in an egg actually do change when you cook them. And this is a fine point. This is not an easy point to make. You may not know what those molecules are and how they change, but they definitely look way different than water going to ice, especially since that's a very common example of a physical change, going from a solid or a liquid to a solid. This is not going from a liquid to a solid with the egg. It's more like, okay, so let me just skip to the end. This is a chemical change. Okay, you can put a C there. I wrote it out to make sure it was obvious. And it says cooking an egg. Why is that like a chemical change? Because it has something visibly very different than what you started with. There. Okay, so I know my handwriting's awful, but that's my sentence that describes why cooking an egg is chemical, because it was, some of the parts were clear and then they turned white, which means that there was something completely different being made there. It was changing into something else. Then there's another part that says the mixing of ingredients for a cake. Now, yes, when you mix ingredients for a cake like flour and sugar and salt and an egg and milk or whatever, like water, whatever you're putting all together there, those things do look different when they're separate and then you put them all together, but it's usually not a huge change invisible. There's still like, okay, water looks wet and so does the cake batter, still looks kind of wet, and that's because you're combining. It's physical because you are combining physical properties but not producing new ones. So it does look a little different, but because no new properties are being produced, there's nothing that is like wildly different. You start off with, like, let's go to the next one, rusting of a nail. Is that physical or chemical? What happens to the nail? The nail is like silver in color or gray in color, and then it goes to like a burnt orange color, like a brown orange color. That is a very different color. There's silver to brown orange color. So yeah, that's definitely different. You have something new being produced, so that's a chemical change. Okay, something new that's being produced. Dew forming on the lawn. Dew is a result of water in the air condensing onto something that looks then wet. And we know that water, like in a water vapor and then forming like dew on a lawn, is a physical change. It's not changing its structure. Where rusting a nail is clearly changing its structure, and the way you can tell that it's that obvious is because it changes drastically in color. There's definitely something. So anytime that you are condensing, evaporating, melting, freezing, subliming, going from a solid to a gas, in one step. Anytime you do any of those phase changes, it's definitely going to be a physical thing and not a chemical thing. So the rusting of the nail is when oxygen mixes with iron, and they form iron 2 or iron 3 oxide, and that is the actual rust color because it's a new thing with new properties. Okay, let's take a look at some of these other things. Notice, I want to make sure that you guys understand, when we're talking about CO2 not changing, going to CO2 on the other side, and the only thing that changes is that this side it's a solid, and over on this side it's a gas, then of course this is physical because we are only changing its physical appearance. We're not changing the structure. It's CO2 on the left side and it's CO2 on the right side. Over here are the reactants. I'm sure we'll talk about that again, and these right here are the products. Okay, so reactants and products, but we're not changing the actual structure though. And again, when we go from gas to liquid, it's the same thing. Notice that when we go from a solid for sodium chloride to aqueous, which means dissolved in water, that's supposed to say water right there, R, there. That is still a physical. This is one thing that lots of people get wrong. This is a physical change because dissolving does not change the structure. Okay, it doesn't. It changes the appearance, but we still, the water, after we put salt in water, we still taste the salt in the water. We're just combining properties. We're not changing something into something new. That's the key right there. If it's not changing into something new, then it's a physical change. I'm going to keep going here. Identify the following as either a physical property or a chemical property. So are we, okay, if it's a property and it's a chemical property describes how something changes into a new form. If it's physical, it can change shape, it can change this or that, but it doesn't change into something brand new. That would be physical. So gold can be flattened into a sheet. That would be physical because the gold's not changing, it's just changing its appearance. It's not changing its structure. Magnesium reacts with an acid. Reacts is a very strong word that means chemical. Iron reacts with oxygen. It's a very strong word that means chemical. Dissolves in water. This is our aqueous, okay? When something's aqueous, it dissolves in water, and that's physical, like I said previously. Sodium chloride forms an aqueous solution. Again, the exact same thing. These two are the same, okay? Hydrogen gas has a boiling point, melting point. Those are all physical changes, okay? So I'm not going to go through each one of these, but you can go through here, and if it forms something new, forms a compound, reacts, that's chemical, and if it does not do that and changes state from solid to liquid or changes its overall appearance but not into something new, then it's physical. I'm going to move on. Identify the following as either physical change or chemical change. Again, this is all the same stuff. Does freezing describe how water changes into a new substance? No, it's still H2O, whether it's a liquid or it's freezing into a solid. Evaporating, dissolving, corroding and rusting, that's chemical. Okay, then you get something new, just like the iron rusting or the nail rusting. Okay, boiling. Boiling is physical but chemical for burning. Decomposing is again chemical. Crystallizing, that's just coming out of a solution. Okay, when you have salt in water and then you get rid of the water, the salt crystallizes. That's not changing its structure. It's still NaCl. Condensing is again another physical thing. Exploding, of course that's chemical. It sounds chemical. Okay, it's very chemical. Forming an aqueous solution, we talked about that. Subliming, I already talked about that. If you need to rewind, then you should rewind. It says, give the particle diagram representing 4 molecules of a substance. Okay, so let's take a quick look at this. If I have an atom of one element and an atom of a different element together in a compound, okay, it says, given the particle diagram representing 4 molecules of substance, which particle diagram best represents the same substance after a physical change? Okay, the same substance after a physical change. Notice that they're floating around, so this might be a gas, when at the bottom this might be a liquid or a solid. So here is your choice. See here, these two are broken up. The compounds, if you break up the compound, it's not the same compound, it doesn't have the same properties, so it can't be that. Notice here, we don't have the same elements mixing together, like bonded together. So this is something completely different. This is chemical, and here again is something that's chemical. Anytime we have circles, whether they're white or black, and they're touching each other, that's a chemical bond. So this right here is a new compound. It's different than this. So all three of these are chemicals, chemical changes, and this is the only physical change because we have the original thing that we started with. The structure doesn't change, means it's physical. Moving on. Standard temperature and pressure. Okay, we need something that at STP, this is a very common standard temperature. Standard temperature is 0 degrees Celsius or 273 Kelvin. I don't mind telling you this. I forget what the table is. I think it's on the very front. I'm almost positive it's on the very front of that sheet. So it's either table A, B, C, D, something like that. I don't know which one it is, so you're going to have to check that out. The standard pressure, though, I can tell you, is 101.3 kPa or 1 atmosphere. Okay, these are you need a condition with temperature and pressure so that we can say it's standard. It's something that we report our information in. So if I say water has, a density of 1.0, this is why I would use this. This is water has a density of 1.0 grams per milliliter, and that is at STP. Because if I change the temperature, it changes the density. If I change the pressure, it changes slightly the density. So we say we report all densities at STP, 1 atmosphere and 273, okay? So in your own words, summarize what STP is and why it's necessary. We need a condition that we can report all of our information in so that we can compare things because they're all at the same place. They're all under the same condition. The same condition of the same temperature and the same pressure. So we can compare the density of steel to the density of water because they happen at the same temperature and pressure. Okay, see what you can do to answer this question with what I just talked about. So description, so melting point, here's melting point. If your temperature is lower than the melting point, then it's a solid. If your temperature is higher than the melting point, then it's a liquid. But if it's lower than the boiling point, it's still a liquid. But if the temperature of your substance is higher than the boiling point, then your state is a gas. So when you take a look at bromine, bromine is red and brown in color. That's a physical description. The melting point is -7 degrees Celsius, and the boiling point is 59 degrees Celsius. So when we look down here, again, I'm not going to do all of them, but I will help you with this. Which colorless substance is a liquid, which colorless? So we're talking about either ethanol, we're talking about neon, or we're talking about water, because those are the three that are colorless. So which substance is a colorless, which colorless substance is a liquid at -30 degrees Celsius? We know that's not water because water is at -30, it's over here on this side, which means it's a solid. So it's a solid here. So solid on this side of the melting point, liquid on this side of the melting point, and gas on this side of the boiling point. So this says which colorless substance is a liquid at -30 degrees Celsius. So neon, what's neon? Where's -30 here? -30 is way over here, which means that neon is a gas because you have -249 and then -246. So absolutely neon is a gas at -30. It has to be because -30 is way to the right of -246. What about ethanol? Ethanol is a -117 here, so on this side here it's a solid. And then where's -30? -30 falls in between -115 and 78, which means, bing, 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 ethanol is our liquid. Did I spell that wrong? I did. I switch those all the time. There it is. It's ANOL, not ONAL. ANOL. Good. So, and it's not EN. Wow, I really screwed that up. So ethanol, there. So which color, so let's do this next one just to see if we can get it done. Which color substance is a gas at 6 degrees Celsius? So which color? Still, again, the same ones. Let's do a different one. Which element is a liquid when mercury boils? So where does mercury boil at? Mercury boils at 357. So that means I need a substance that is a liquid less than its boiling point. is 357. Do we have any boiling points more than 357? And the only one is this one here. So 357 comes in between 115 and 445, so the last one here must be sulfur, and that is UR at the end. Okay, let me just check to see what we got here. Some physical properties, including melting and boiling point, the first 92 elements are listed on table S, the reference table. Suppose you were at Boston, Massachusetts, sea level, and it was cold enough to freeze water. What state of matter would each of the following substances exist at? You have to look at table S, and the melting point and the boiling point. If it's the left of the melting point, if it's less than the melting point, it's a solid. So it's asking for which state of matter would you. So hydrogen would exist because 0 degrees Celsius, now 0 degrees Celsius is equal to 273 Kelvin. And if you notice in table S for hydrogen, the boiling point is very, very, very low in Kelvin. So this would, of course, be a gas. Okay, I forget what it is. I don't have table S in front of me. But I can tell you that if you take a look at hydrogen's boiling point, it's very low. I mean, literally like 5 or something Kelvin. I forget what it is. But 273 is way to the right of that, which puts that firmly in the gas. So take a look at lithium and also bromine and do the same thing. Find 273. Does it fall to the left of the melting point for lithium, to the right of the melting point, but to the left of the boiling point for a liquid for lithium, or to the right of the boiling point, which means it's a gas? At STP, which list of elements contains a solid, a liquid, and a gas? Okay, you're going to have to look on the table S to figure that one out. And then each one of these is at STP, which means standard temperature is 273 Kelvin. So this is all happening at 273, so you would look at HF, see what state of matter it is at 273, Hg, see what state of matter it is. I can tell you this one is gas, I can tell you that. I'm not sure about Hg, and I'm not sure about HF, but you do that for each one of these to find out which one is a solid, liquid, and a gas. So you have all 3 states represented in each group. Find out which one has a solid, liquid, and gas in the whole group, and then circle that. Okay, where are we at here? That's it. Okay, this is a long one. Sorry, this is a long screencast. Hang in there. I'm sure you'll do a good job.